All right, how's everyone doing? Okay? Yeah? You must have some classes on Monday, right? Or none? Yeah, you have some classes on Monday? Okay. But this is our last session together, and we'll have an exam on Thursday at noon here. Okay. Any questions administratively about the exam? Yes.
How long is he? Why is it?
Right. Good question. I am not exactly sure how long it will take, but I think you will probably, plan on at least a couple hours. Okay. So, yeah. Is that helpful? Probably not that helpful.
I was just trying to think of it. If it's going to go on the entire 3 hours, because that exams, college have right afterwards.
Okay.
And that teacher's crazy.
Okay. So, yeah, okay. Well, we'll keep it in mind as the exam gets, um, yeah, formalized. All right. Good. Other questions administratively? It is from 12 to 3. Okay. Okay. So today is the kind of final set of ideas we're going to talk about in terms of beam bending. Okay. And specifically looking at deflection of these systems that have moments or forces being applied to them as you move along the beam. Okay, and there are multiple ways that we can tackle these problems now. We have, well, we'll look at them. So if we're talking about deflection of beams, okay, we have the integration methods, right? So integration methods refer to taking this equation at its different levels to be able to integrate up and solve for the appropriate boundary or appropriate constants when we do the integration with appropriate boundary conditions and continuity. Okay. So going up, we can say that we have that, and then going up one more level, we can say we have that, right? And then if we're interested in getting to slope along the beam, right, we have to integrate that equation, right? And then if we want to go and get displacement, we integrate a couple of times. Okay, so this technique is pretty useful. It's very useful, in fact. It tends to require a lot of algebra, and so someone like me, prone to make mistakes. Okay, but it is out there. Okay, and we should be expected to do it. Some of the key things to keep in mind here are what are the boundary conditions that we're interested in, right? So boundary conditions are typically going to be looking at when is the slope equal to 0, right, at different locations. When is the displacement, the vertical displacement, going to be equal to 0? Okay. And you can have boundary conditions as well for the moment and for the shear force, but it's probably safer to remember that, and these are related. It's probably safer to remember that dv dx is equal to w, and that dm dx is equal to v. Okay, probably not. Maybe not always. If it's a problem where there's just a distributed load across it, maybe you want to go 4 derivatives deep, or 4 integrals. It's up to you. But so in those cases, if you start, with a distributed force, then you will be looking at situations where you are looking at big V, right? Maybe equal to 0 or something else, or constant, right? And big M, or Rm, equal to 0 or constant. Okay. So those are some things to keep in mind. Now, with continuity, what happens is we are sometimes having a break in the beam because there's some type of applied load, okay, or there's a support, right? So in those types of situations, even for something that's kind of straightforward, right, where you have something like this and there's a force being applied, okay, it's probably not a bad idea to go ahead and say, oh, well, I guess I've got to do an x1 maybe that direction, I got to do an x2, we'll say from over here, okay, like that. Now, continuity is saying, hey, what happens when these regions meet up with each other? Okay, so it may often be better to say, okay, x1 goes, until you get to the middle, x2 goes until you get to the middle as well. So the types of continuity conditions that you're typically interested in involve v1 at, let's say this is, well, things of this nature, right? So that you get L over 2, you get L over 2, okay? And then these are little v's, right? The little v's, maybe I should be more careful just so that there's no mistaking here. Well, that's not the bestest. Okay, so these displacements are going to be equal to each other when we get to this interface between the two. And then the one that's a little bit confusing, but you get used to it, right, is that if they're coming from opposite directions, then the slopes, all right, slope, this is are going to be opposite. Okay, that's the convention that we're using, and it keeps things straight. Okay. As you go through today, you'll also learn about superposition, which is extremely useful for these types of problems, and learn about how we handle indeterminate systems. Just a few words on indeterminacy. I used to get confused, and I probably still do, but I think less so, about indeterminate systems and how you determine the degree of redundancy. Okay, and I go through it in the notes, but here, just if you have questions, we can talk about it. But with indeterminate systems, I think it's, instead of thinking number of unknown variables and number of equations, I think it's simpler to think of what can I remove from this system to get to a determinate system, okay? And maybe, so in that case, we have to define what is a determinate system. So a determinate system, all right, so before we get to indeterminate, we say, okay, determinate system right? This satisfies static equilibrium. And if I were to take away one of the reactions, it would no longer satisfy static equilibrium. Okay? So, for example, we've been looking at this case. Okay? If this is a statically determinate system, because if I remove either one of those supports, this thing is just going to flop over, okay? And it's going to be a pendulum, essentially. So this is determinate, right? I can't, if I remove, it becomes a dynamic system, okay? So an indeterminate system can be thought of, and then maybe here's another example, right? Classic cantilever. I guess I have to put a load on it, because if it were in microgravity, it might not, it still might not move much. Okay, but you know, cantilever system, another one. It has two constraints here at the wall, the moment and the force, so it's statically determinate, right? If I were to, you know, make this, right, it's the same kind of deal, right? If I take away the moment restraint from the wall, right, this is just going to go whoop, and it's it's not determinate, not statically determinate at least. Okay. So when we look at these indeterminate systems, the name of the game is how many of the supports, the reactions, can I remove to get to a determinate system. Okay. And so, you know, if we have this system, we know it's determinate. Okay, that's determinate. We said it. If I add this, that extra roller is not necessary for determinacy, and it actually throws a wrench in my gears, right? Because now I've got more unknowns than I have equations of equilibrium. Okay, and you can watch that, you know, and so I can keep adding things, all right, like this, to make it more and more indeterminate, essentially, right? So if we have one of these, that would be redundancy degree 1, okay, or degree 1 of indeterminacy. This is like degree 3 degree, or degree of 3 in its indeterminacy. Okay, because I can remove those 3. And if I remove any one of them, if I remove one here, or I remove one here, or remove one here, then I get to degree of 2. So what happens when you have an indeterminate beam bending problem? Well, it doesn't mean it's not solvable. It just means that we have to be a little bit more careful. Okay? It means that when we write out when we do a slice, for example, okay, that we could have an unknown or 2 unknowns or more unknowns, and so we need necessary boundary conditions. We need boundary conditions or continuity to be able to knock those out when we do the integration. Okay. With superposition, what it can mean is that we need to look at equating displacements okay, in these different regions with each other, or displacements at a location, okay, or angles or slopes. Okay, so if we're doing method of integration, which is EI whatever, that kind of stuff, then we just have to use, we're just constantly keep track of boundary conditions. Okay. If we're doing method of superposition, then what we have to do is look for opportunities to use compatibility. Okay. Compatibility. Okay, that's right. Okay, so that's the kind of thing back in the day where we said, oh, if I have and I'm applying some force, right, to the bar. This is an indeterminate system. Yeah. And so this was the opportunity to say, oh, well, this can equal this system, okay, where that's a force being applied to it, and I have some displacement now, okay, so I have some displacement up called delta 1, and I've got to have a reaction force on the bottom at the bottom that gives some extension to compensate. Okay, and so what we're looking for is essentially a delta 1 minus a delta 2, okay, which is going to be equal to 0. Right? I need delta 1 and delta 2 to be equal to each other. And so this is an example of compatibility. So with beams, with beams, we can go beyond. We can say, oh yeah, we can have like V1 or a V at A is equal to a V at A, right? But we can also have things like the angle at A is equal to the angle at A, right? Or something like this. Let's say we have, this is just an example. Okay, this is another example of an indeterminate system. Okay, so it's indeterminate. What would I do? I'd remove the roller to make it to make a determinate system. Okay, and so what we can think about here is, all right, I can have this beam going over like this, with P being applied there, and we can say now that we have some displacement. Okay, at the end, we'll call that 1. Right? And we have another system where we're going to put a force at the end. Okay. We'll call that maybe a Q. All right. And that Q is going to tell us that we have some delta 2 here, right? And we need that delta 1 because of this condition. Delta 1 minus delta 2 has to equal to 0. Okay? And then when we do that, right, we know P is a known. We can, yeah, so watch me botch this up. Well, I don't know off the top of my head. I know this one. So delta 2 is equal to QL cubed over 3EI. Okay. This one, I want to say, but I don't remember what it is. I think it's something like 5PL cubed over 48 EI, or maybe it's 3. I can't remember. This is question mark, right? But the point is, right? The point is that you equate these to each other, so that you get this equation, and right, and how many unknowns are there? Just one, the Q. Okay, so then we can solve for Q. If someone can fact check, I don't remember what this one is. Okay, when it's at the middle, this is L over 2. Okay, anyway, it's in the notes. Okay, so that's and then the last technique is to think of beams as springs, right? So beams as springs, and when we do that, what we're essentially saying is, for example, I have this delta is equal to the QL cubed over 3EI. I'm thinking, all right, well, F or Q is equal to K delta. Yes, Dean?
Where are you getting these numbers from? Like
These?
Equations that equal the displacements?
These right here? Okay. So these are coming from pre-solved problems. Okay, so, okay, fine, I will pull it up. We have tables, so if you look, okay, so here you go. Vork and others have gone through and calculated out equations that describe the displacement in different situations. So for example, this is a pinned beam with a P being applied in the middle. Okay? And so what you have, and what I'll give you sometimes on an exam, and if you look at previous exams, you'll see, this is the condition, all right, that you have. But it's not the, well, maybe the first problem is like, okay, it's exactly this, you just plug and chug. But what you have are different types of conditions for statically determinate systems, okay, or beams, and then you combine them for solving these statically indeterminate. Or it could be other statically determinate systems, actually. It doesn't have to be statically indeterminate. Okay, does that make sense? So this one's kind of a famous one. All right, so it's a point load in the middle, pin. All right, and so and they're using different nomenclature. We use V. Okay, they're using W here. All right, but the displacement at this location is going to be PL cubed over 48 EI. Also, and so you could solve this if you want, Dean. Every time you could do method of integration and you could solve this. That's a waste of time, unless I say that's what I want you to do. If I say use method of integration, then you're going to use method of integration. All right? But if we want to try to use superposition, then I would give you something like this. Okay.
More likely to just do that and tell us to use.
So if you're an engineer, a real engineer, you're definitely more likely to do this than go to the method of integration. Okay, and um, so yeah, so here, this is the cantilever case that I was just doing. P right at the end, and I actually got that equation right. I said it's PL cubed over 3EI. Okay.
And the Q is shear here.
The Q is shear, that's correct. But often for these problems, we want to stay out of shear land if we can. All right, we want to avoid that. Okay, we want to be looking at the moment if we're doing integration. I mean, if you have to, you have to, right? And I did an example in the previous session 24, where like we did 4 integrals, all right? But if you can avoid it, avoid it. Start with the moment. Get an equation for, because especially if it's a statically determinate system, you know you can figure out the moments across that beam without too much difficulty. Okay. Yeah. Yep. Yeah. So then I was looking for, yeah, like for this case, okay. This one, yes. Oh, was I actually right? I was actually right. Huh. Okay. So the displacement delta P, all right, with P's applied in the middle, it actually is 5PL cubed over 48 EI. Did I say that? I did. 5PL cubed over 48 EI. All right. So using superposition with these different configurations, all right, and superposing them allows us to solve for an unknown reaction, okay, and a redundant reaction. So Q right here, that's a redundant reaction. And then once we solve for Q, then we can go back and we can look at things like, okay, what's the displacement across this beam? And so for that, you don't want to use these equations because those are just at the end of the beam. Okay, what you got to do, or what we get to do, is look at equations like this. Okay, so this is the V, right? So this is V at C at the right. Okay, so this is you can't see this. Okay, so this is V at C, this one right here. So that's the PL cubed over 3EI out here. That's describing the displacement of the beam. The other equation, though, is more general. This would be like little v of x, right? And so to get this, what you do is you plug in x equals L over here. Okay. But if you want to know what's going on halfway across the beam, then you plug in x equals L over 2. If you want to know what's happening at a quarter of the way across the beam, you plug in x equals L over 4. Okay. So the last couple assignments, I'm spending a lot of time on this. This is, I guess, a little bit abnormal because normally we just let you do your thing. But we haven't had an exam on this material, right? So let's talk about the final exam a little bit. Going backward, working backward, right? So the final exam, we haven't had any questions yet. I mean, we have homework questions, right? But we need to do something on beam bending deflection, right? So you can anticipate there are going to be questions on deflection of beams, okay? It would be mean to, well, it would be mean, right? It would be mean to do, okay, what would be mean? And I don't mean average. I mean, this would be mean, all right? To do problems where we have method of integration, with multiple regions, right? Okay, like, in fact, I made a boo-boo on the last homework, right? And Michael did it correctly, Okay, that was a multiple region problem. Okay, I was trying to take a shortcut. I was trying to say, oh, I can see where the slope is 0, and then I don't have to do all the algebra. No, it was not right there. It's a little bit over. It wasn't the moments. Anyway. It's
What, are you talking about question 2?
yes,
Okay.
yeah. I was talking about question 2 on session 24, right? I tried to do a slick shortcut. I was like, this is slick. It was slick, but it was a little bit off. Okay. Okay. What is very possible though, and reasonable for a method of integration, that you could find yourself looking at a system with a distributed load across it. Okay? This is fair game. Why is it fair game? Because you only need to use one x as long as there's no point load on it. Okay? And so I don't think you want, and you could, again, you could go all the way back to sorry. Okay, we could go all the way back to this equation, all right? But it probably makes sense to think more in terms, and this has got a W across it, right? It probably makes more sense to have an effective point load, right, being applied here. And this is, what is this? Is W naught X, right? That's the quantity of it. And what is it doing? It's acting at a distance X over 2. Okay. And there's a reaction down here as well. Okay. This is very reasonable. Okay. But for more complicated situations, okay, with beams, or let's just be specific. For statically indeterminate cases, then I don't think we'll do a method of integration for a statically indeterminate case. It would be a superposition problem. Superposition or beams as springs, right? So we have a flashback to exam number 1 from this semester and last semester with a statically indeterminate system that was pretty much, they were identical, okay, but that was with normal forces and thinking of bars as springs, okay? So beams as springs is a thing, okay? So I would be knowledgeable on how to do these. Okay. All right, and so that, and then in both cases, well, actually, so in this case, deflection of beams, this is we're saying this is a single region, statically determinate. Case. Okay. In the statically indeterminate case, okay, we might have to, well, we will have to find expressions for redundant reactions, right? The statically determinate case you are going to know all those reactions, okay? But in the statically indeterminate case, we can use superposition, or we can use beams as springs to be able to figure out what redundant reactions are. And then once we know what redundant reactions are, then we could go back and say, okay, what's the displacement? Actually, with beams as springs, you don't even you can get away without having to figure out those redundant reactions. Okay, you can just go right to displacements. Okay, so that's deflection. What did we cover right before? That was not on exam 2. Failure criteria. All right, so failure criteria. Definitely fair game. I'm not a big fan of more criteria. Okay, so I mean I could do it, but I don't think I will do more criteria. Okay? Because, well, there are a couple of reasons. One is the brittle. I mean, just maximum normal stress is simpler. All right, and it's simpler. I would say don't worry about more. But definitely no max stress or max normal stress. Okay. Because, and this, well, not because, these are criteria for brittle materials. Okay. The other criteria, right? Ductile materials, most definitely. Okay. It'd probably be strange if I didn't do a von Mises problem. Okay. So, but it could be, I don't know, you know, but I would say that you want to know ductile materials. Right? And so with that, we have von Mises. And I think the thing to remember with von Mises is it actually is trying to make your life easier, but it might get a little confusing, right? So with von Mises, we come up with a sigma equivalent. This sigma equivalent is what we're comparing to the yield strength that someone reports from a material, right? And the sigma equivalent, if you have the principal stresses, and I'm just doing off the top of my head, so I hope I'm not making a mistake, but I probably am. Okay, it's something like this. All right. Now there's the other equation you can use that I'm not going to try to write out. Okay. That one. This is just with principal stresses. Okay. And so the deal is compare to the yield strength. Okay. Now, yeah, we can get into the fact that this is based on distortion energy, and we could, but I'm not going to ask you to tell me what the distortion energy is. Okay, that's not a very common thing. But yes, we need to know the equivalent of von Mises. We need to know if it's less or more. And then the yield strength, and we need to be able to do this with safety factors, right? So safety factors, as we saw, right, in the assignment, deceptively not simple, right? Or I don't know what you want to say, right? They can be a pain, right? But they're important, okay? And so compared to SY, you know, and considering specified safety factor. And, you know, one other thing to know about the von Mises, right, is that on a sigma 1, sigma 2 plot, this is not more circle, right, that, you know, you put out the points. Yep. That's probably about right. That's fine. Bless you. That's a crummy looking. That's supposed to be an ellipse. Okay. There are cases where we're interested in the pure shear. Okay. So pure shear is often cited here. Okay. And the maximum you can have in pure shear for von Mises is going to be square root of 3 over 3. Okay. Sigma 1, comma, square root of 3 over 3 minus sigma 2. Okay, and there's also one out here as well. Okay, so that's a pure shear case. If we're looking at pure shear and it's pure shear for Tresca, right? This is max shear stress. Then what we have, sure, why not? I'll just draw it here. This is, what color should I use? Right, Tresca looks like this. So pure shear for Tresca, I already wrote that, pure shear, right? That happens at sigma 1 over 2, comma, minus sigma 2 over 2, right? And this makes sense, right? Because if we go back to the Mohr circle, this is the uniaxial case, right? This is SY there, right? Sigma 1 is a uniaxial, sigma 2, sigma 3 are 0. Okay, so the maximum normal stress, right, the tau absolute max has got to be equal to SY over 2. Okay, so yeah, you're like, oh, it's a little bit counterintuitive because I have a uniaxial load that I care about when I do the test for the yield strength, SY, right? But if we have a ductile material, we're thinking about the absolute maximum shear stress, and that's our metric. Okay. So anyway, but if you're doing the von Mises criterion, then forget maximum shear stress and make sure you set the sigma equivalent. You're comparing that to the SY, to the yield strength. Okay. Any questions on this? Okay. For Mohr circle, we hadn't done absolute maximum shear stress yet. Okay, and so that's related to Tresca. We had gotten to in-plane max shear stress, but we hadn't gotten to absolute maximum shear stress. Okay, so that's where we are going to be kind of differentiating. Not yet. We'll get them in a little bit. Okay. Okay. Then before that, if we go to, well, let me see. Let me just take a look at what we've covered. Okay, right. So strain gauges, right? We also did cover strain gauges in the last little bit. Okay. Don't worry about 60-degree strain gauges. All right. Okay. I think do know how to do 0, 45, 45 strain gauges. And you can do the transformations, right? But this gets to strain, all right? So remember that with strain, we can draw more circles as well. Okay? We have transformation equations for strain as well. And we want to make sure that we have the appropriate axes where now we're dealing with gamma over 2. Okay. This is Moore's. Okay. Yes, combined loadings, definitely fair game. Okay. Flexure formula. And yep, torsional formula. Okay. And yeah, we should be able to do some angle of twist. I know it's a pain, but we should be able to know. We should be able to do some of that. Okay. All right. Any questions? We didn't cover thermal on any of the exams. All right. I don't know. We may not cover it again. We'll see. But it's a possibility. There's too much stuff to cover on the exam. Right? There's just too much stuff to cover in 3 hours. So we'll be reasonable. All right, so yes. I don't know yet. I don't know. Matt, yes? Yeah, so it's 3 formula sheets, handwritten notes on both sides of all 3. Okay. And you can write anything you want. Yes?
What's the most common mistake you see on the exam, or a mistake that you see on the exams?
You want to weigh in on this?
Carrying the negative. If equation has a negative, a lot of people just write the equation with the negative and just never carry it through. Units, make sure you write your units. That's pretty much it. I think this is probably the most common one where I've been pretty lenient with it, which passed 2 exams, but for the final I will try to, I will have to deduct points, unless it's very obvious that you just simply forgot it, but really you should, units and positive, negative.
Yeah. Right. I mean, we've been pretty. Yeah, I think that's one of the nice things about this class, actually. Well, it's one of the painful things about this class, right? But people are now. I mean, when I say gigapascal, what are you thinking? Like, huh? 10 to the 9th, yes. And then what are the only things that we deal with pretty much that are gigapascals? Yeah, elastic modulus, right? Nothing else. Elastic modulus, shear modulus, right? So I think we got that point. When you hear megapascals, a whole bunch of other things come into mind now, right? Like what are we thinking about with megapascals? What are some of the quantities? Huh? Yeah, so it's definitely stress, yes. That's true. We're also thinking about yield strengths. Okay, so a lot of the yield, right, by now you should see the real materials, the ductile ones that we're dealing with, and the brittle ones, you know, on the order of 100 megapascals for yield strengths, right? Whereas aluminum, 70 gigapascals. Steel, 200 gigapascals, right? For elastic modulus. Elastic modulus, gigapascals. Yield strengths, or even ultimate strengths, either compressive or tensile, megapascals. And often hundreds of megapascals, right? More circle, hundreds of megapascals, okay? When you hear microstrain, or you hear micro, right? You're thinking, okay, now 10 to the minus 6, and I've got, you know, maybe hundreds of microstrain. Okay. When you see microns, or micrometers, right? You're thinking displacements, okay? And that's 10 to the minus 6. Okay. When you hear kilonewtons, you're thinking forces, right? And you're thinking, okay, that's within the realm of possibility. Okay. We haven't done, often we're in hundreds of Newton meters. We're not usually getting up into the kilonewton meters. Okay, that hasn't happened too much. And I've probably spared a lot of us from using imperial units this semester. The book definitely goes, Hibbler's book definitely goes back and forth between them more. And there's some good conversion factors that we should be familiar with. Okay, so we haven't had so much on KIP, right, or KSI, right, but know that KIP is 1,000 pounds, one KIP is 1,000 pounds, one KSI is 1,000 pounds per square inch, you might know that one KSI is equal to 6.89 megapascals. Okay, so there's the ability to convert between these units. Okay. Other questions? Is there a topic you really want to have on the exam that you're like, hey, if he gave us that, that would be really nice?
Unit conversion.
Unit conversion. All right, that was like, I mean, look at how far we've come, right, from the beginning. I think you guys have come a long way, at least in that respect, and other respects too, right? But like at the beginning, there was all this shouting and screaming on GroupMe about, oh, the unit's this, the unit's that, and now it's like, yeah, dude, you got to multiply by 1 times 10 to the minus 6, right? That's like how the GroupMe unit thing. Yeah. Okay. All right. Well, go ahead, work on the problems. I'm gonna go to the car and get the exams that people are wanting to have back. It's been a pleasure teaching this semester. It's been so painful though, so painful. Okay, I don't know if I've ever got as little sleep as this semester on teaching. The move to YouTube, the move to actually having reasonably good notes, okay? All these things were very painful to do, okay? But I'm hoping that I will be less painful as an instructor subsequently because of what the pain that you have endured in this as well. So that said, yeah, there is the survey on the course. Be honest, all right? Tell it how it is. Preferably don't be too mean, all right? You can be honest and kind. Those things can coexist, right? But yeah, there are a lot of things that I'm hoping to keep doing in the future for this class. And there's some things that, I don't know, we'll see if they continue or not, all right? But I appreciate you all sticking with it. And I hope that the final exam is an experience where you're like, okay, I did learn this. I know something about whether or not something's going to break, okay? I know something about how to do these stress transformations, and Mohr circle is now kind of intuitive. I have an idea of how to calculate displacements. I have an idea of how to calculate strains. Okay? If someone hands me a piece of material and gives me elastic modulus and a Poisson ratio, I can figure out, if I stretch it, how it's gonna respond, right? These kinds of basic things are what you want to be taking away and using in the future. You know how to do some finite element analysis, okay? Not very well from what we can tell, but you know some, all right? And it was not the emphasis. And it's partially my fault. I shouldn't criticize you guys for that, all right? But you've got a taste of it, right? And so that's also another valuable thing that you can take forward as you move move through different classes. All right, so good. I'll be back in a few minutes. Go ahead. There are only problems 1 and 2 right now. I have to get problems 3 and 4 up there. I think I have to have everything due before the reading period. So right now things are set to be due Monday at 11:59 p.m. Okay, I'm not sure about that, but I think that's kind of the rule-ish. If you want to take advantage of getting up to 4 extra points, fill out the survey. You can already do any of those other problems, okay? Because the way it works, right, is they're still all accessible, okay? The thing is, though, that, of course, Canvas will penalize you in this class. If you do anything from, like, over a week ago, essentially, you would get 0 credit, right? But then what we'll do is we'll go back through and we'll release those penalties, so you get whatever that point is. Those points are. So 4 points. Okay. Good. All right. I'll be right back in a couple minutes. Thank you.
So the professors have it class just typically whatever you say average once weekly, then whatever you got. Single mother exam 2, exam 3,
So I completed the form a while ago, and I don't remember what it was. Is there a way,
for the orange ones, this was known as the results. So, yeah, you have to wait. So he hasn't given me the results of the form. So I have like when the results, when you do the results, you should see it before May 1st. So whatever you put in for assignments, make sure you already did them by May 1st, and then I'll go through it and I'll just remove all the late penalties. So whatever grade you got for that, I'll see.
$5. $5. You don't take it out. So since it's loose and since this tip is flattened out, there's a kind of a notch. Yeah, of course, at this point, but I'm just illustrating.
Yeah.
Okay. You lost that right, and then well, you say that, and then you say that, so you just combine it.
You do.
Yeah. I was gonna make it happen, so basically,
The rest is just back like this. Yeah, that's
oh,
here all the time. Just to cover all the
Quick question. What is, like how example was where it's just like variables and you're working with variables? Or are you gonna have both? Okay. And you didn't say, I mean, you're not sure.
Bring your first name. It's confusing for that, but it's alright, you know. It'll be on for the
Thank you.
Good.
Have a good weekend.
You too.
Oh, this thing. Two.
I'm not ready yet.
Yeah.
I'm probably getting ready.
Yeah.
I'm probably gonna start nothing. I got like my last show. So that's not that.
Oh, it's nice. Where you guys playing?
It's called the Black Lodge. It's on Secret Street. Yeah.
I thought Kirk had theirs last year.
Yeah. It's on the same street.
Oh, is it? Oh, okay.
It's like a, yeah, dude, it's awesome. Bring like a old book or something, and then you get it for free. It's for like a fundraiser.
Oh, really?
Yeah, yeah. It's like,
You teach
it's
any
like
of
five,
the
like, you could just my band's playing at like 7:45.
7:45?
Oh, I'll have you next.
Well, no, I don't think I'll be doing it next time. But VMC.
Dude, they need drummers.
Yeah.
Yeah, they always need drummers. Because they get,
I've never
every
seen
level,
level.
because just everyone is fucking dad plays fucking guitar. No one plays drums.
No, because I see that, like, on video, you check the basement show, but like, I get, you know, with bouncing with school, I'm just sitting there.
I was nervous when I was freshman, but I just started doing it. I just jumped in, like,
do it, and
then again, I had a head start because I already had my band for like 3 years in a row. You know what I mean?
So there was less
we
band?
we were tight.
I was
We had-
close.
we had
My friend took it last semester.
You know what I mean?
Do a lot of the original stuff?
I'm pretty sure you told me that was teaching it, but I could
Yeah, yeah, I know a really good band. Yeah, so they're called ER. Super tight, and it's literally just a guitarist and a drummer. It's awesome. Yeah, and the guitarist sings too.
And then what do they do? Do they just have a set here and then?
And for standings.
Later, but
We changed it later.
It's like, yeah, they have like a house set, And like,
I don't know.
they sometimes they ask you to bring your own, like, your own. I think you're allowed to use their samples usually, but
there are a
like,
lot of other
it's different at every venue. Sometimes you're like, oh yeah, our snare sucks. Like, can you bring your own? Or like, our clutch is broken.
Do you
something like that.
teach any of
You know
the?
what I mean? So beyond the set, like, you know, sometimes they just ask you to bring one or two.
Yeah.
Dude, that's like, if you just go into the shop and you're like, does anyone need a number? I guarantee you'll get some hits, and then like, you could at least connect with those people and see who might, you know what I mean?
Yeah.
Your first year teaching your records or no?
No, I didn't. I could, I mean, even though the stuff is okay, it's my sixth year in fall. So this is the gospel.
Yeah.
Did it differently? Okay.
Yeah, I don't know why this class is so hard for me to understand. Like comparatively, to, like everything else, I think it's just so different.
Yeah. It's
It's very different. It's so different.
Oh, yeah. So,
I have his permission.
Yeah. I was gonna say Jeff Hansen, I watched all the videos.
Yeah, I think that's
They do help a lot, like the flexion one. I only got an advanced calc and seeing boundary conditions right now, I'm like, oh, I kind of know that.
yeah, so, I mean, we haven't really strayed too much from what's typically covered in, you know, this class. Thank you very much.
Yeah.
Yeah, no, I mean, we should all get together maybe next week.
Yeah.
Yeah, the last time I was just like,
No, for real.
It's like a hard thing to explain. Conceptually, like those videos you posted, I don't know what they are. Like I understand them like conceptually, but then I get to the math of it, and I don't know why it's like so much harder. You did a good job like conceptually as well.
Thank you, Professor.
Thank
Have a
you.
good one.
See you later.
Yeah, I think that may just be off like me not doing enough practice.
We're still figuring it out. Still figuring it out.
Yeah, I already have the second exam, but I just wanted to make sure before I like asked it. I don't want to send them on like a wild goose chase. Yeah, dude, I got your
So, like Jeff Hansen
Are
goes
you,
over
at your barber?
problem, it takes like 20 minutes. Yeah, 20 minutes for one problem. And it's like if you were to lose that here, it comes with like one problem for like the whole entire class. But I like to do
Yeah, that's
it.
cool, man.
Maybe not. Yeah, I mean, that's
No problem.
these videos and stuff.
Exactly.
Their videos and videos here. You can go through them and stuff. Yeah. It's also some of the first classes that you take as an engineer. So
Yeah, it's like a degree class. So it's like it really amped up.
yeah. So I don't know what other campus classes have you taken.
I took statics, we're in dynamics together.
Statics is like everything.
Statics. I took, well,
This is my first, other than I'm with mechatronics right now. We're just got deal with this week.
Yeah. So yeah, like once you take fluids, they're this stuff is complicated.
Yeah.
It's complicated.
Yeah.
As much as you say.
especially
Like yeah, I
first time looking at it, you didn't have to understand it, but like I'm working with
Have a good weekend.
equation and wave equations and stuff. Equation, and it's just like the same thing. Yeah, just a little different.
Yeah.
Different styles to approach it. Yes. That's that's the first.
Yeah. Of course. Thank you.
Yeah.
It is, but I go by the middle name, so Tyler.
I was happy that you got my name when I raised my hand. Thank you very much.
That is okay.
How can I know this ever? I'm so sorry.
No, you're good. It is right.
Oh, it is.
Yeah.
The one with the curly hair glasses.
Yeah.
I get confused. It says Riley, like, Todd, like,
Riley, Robert, Tyler.
Yeah.
that's throwing me off. So I'm like, you're not Riley.
No.
And anyway,
It's complicated.
no, it's not that complicated. It's really-
Well, you have a lot of people to remember, you know, so it adds complexity. I spice it up.
Well, good. Good. So, good luck on the exam.
And then, do you have any like labs during the school year?
What do you mean by lab? Like, yeah, our lab is, yeah, we have our research all the time. So if you're interested in sending that message.
Okay.
What we try to do is we try to pair the undergrads with the grad students. So if the grad students are looking for people, then it's good. So it's less dependent on, like, I like people. Yeah, like, oh, I like you. But I will say that if there's a group of people from this class who are interested in creating demonstrations, so that's one thing that's lacking.
For this class?
Yeah, we have
Or just
zero physical demonstrations.
Your chalk one was like the most like understanding. Like I did, you missed it, but it was for like ductile and other brittle materials.
Oh.
The fracturing points. Like that was very useful.
Yeah. So I'm interested in seeing if we can have like examples that are created out of like at-home materials.
Okay.
So like chalk,
Yeah.
food, those types of things.
I know, like, this probably won't help, but, like, I saw on TikTok for Med Materials at a different university, they have, like, a lab, and they were doing, like, the angle twist, like, looking at
Yeah.
the beam. And I was like,
Yeah, so there are some labs that, so right now there's kind of some discussion about whether or not some of the measurements in senior labs should not be waiting until 2 years later when once their labs there that can be coupled very nicely with the material that's being taught. So it can go either way. Some places we try to do the labs concurrently, but other places like us, we've been doing them later. But that's like when I was an undergrad, some classes were just fully and stuff, but some of the most memorable classes are the ones where they brought in demos and
Thank you, Professor.
see you, Dean.
Bye.
Good luck.
Thank you.
And so yeah, so I would like to have like a kind of a bunch of experiments that we could do with the legal costs. And that we can just be done in your teaching.
I know one's like really basic, but it shows you like I guess a bar strength. For like pasta, they took it. Well, it's also material, so it's very different. So it's just like the difference between trying to pull it apart and push it. You get to see that it will fail like under compression a lot easier rather than what's it called? Tension. Yeah. But I don't know. That's all material based.
Well, now you're saying they put pasta and they were bending it, right?
Yeah, it was like an uncooked pasta.
Yeah.
And then there's like applying pressure on the top.
Was it a beam bending problem, or was it
That was like
or was it a buckling problem?
his buckling.
Oh, okay. Yes,
But we didn't cover buckling.
No.
no, you'll cover it in beams.
Oh, that's a DMC topic? Oh, I thought that would be like a neck props.
So it's I've never
It's scary.
gone to it in this class, but in DMC we covered it.
Okay. Huh.
It's in the book. It's in the book.
Yeah.
Read it. Or in the book.
I will most likely reach out. I applied for one for Andy's lab. It was for like a carbon-free material, the Artsy labs. Airscape labs?
Yeah, carbon-free material, like this, was this the material science or was it more than probably a requirement?
Probably, that does sound familiar.
Yeah, okay.
I don't know, I didn't really see not many there for like the art department, so I was like, I guess I'll just apply anything.
Yeah, so I used to do more with the rest and because I just gotten kind of lazy. And, but yeah, that's all it had because I used to do summer science and stuff.
But it's not.
So it's a good deal. It's a great program.
Hmm?
It gets people money.
And
It's just fire.
Alright, thank
Have a good
you.
one.
You too.
See you, Tyler.
See ya. Hey!
Yeah, well, it's like 5 seconds. Sudeep, keep it real.
It's been nice.
It has been nice.
Yeah.
I'm looking forward to getting some sleep.
Yeah. Oh my god.
I'm sure you guys are too. Just a couple more weeks, right?
Yeah.
2 more weeks.
That's all done. Spring is. I remember as an undergrad too. I was more drained by the end of spring than I was by the end of the fall.
No, I actually feel that spring actually is really fast actually.
Okay.
But it's exhausting.
Okay.
It's very exhausting.
Are you invigorated by the nice weather and stuff? I mean, it's great, but I was just like, I need to get out and light it up.
Weather lately hasn't been that great. Other than that one week, it was like
Well, the strike week was a good
The
week.
strike was a miracle. Oh my goodness.
amazing week.
What are you talking about?
I was
Beautiful
melting.
weather. Well, I mean, you could go to the beach. You can go to a nice pool.
It was amazing. It was. I mean, whatever. I was still working, but it was still
I
amazing.
adjusted it.
very windy and
See
See you,
Oh,
see you
wow.
on Thursday.
Perfect weather. I'm gonna solve this. I'm gonna solve this. You'd love this for sure.
Oh, you got